Okay, I think I'm ready too. So let's go ahead. This is week 4. We've got a midterm tomorrow. Please come in, put your backpacks underneath places. Um, get out your worksheets and things that you need. Grab chairs from the hallway. I'm missing a couple chairs. I don't know where they went. And feel free, you can take my chair if you want. I'm not going to be sitting again.
Okay.
I don't imagine.
Let me just check something.
Is that readable? Is that visible? Yeah, that looks great. Okay. So, I know we've got a couple homework questions. We've got a couple concept questions. Someone just asked what material the exam on Thursday will cover. It's going to be pretty much all of Chapter 1, all of Chapter 2. Well, that's not how I want to write Chapter 2. All of Chapter 2, all of Chapter 3, the beginning of Chapter 4, particularly 4.1. Then also Chapter 10.6 question mark. So we're going to cover 10.6 in class today. I'm not sure if I'm going to include it on the exam or not. And then also, before I forget, someplace between Chapter 1 and Chapter 2, we also did 6.3. That's where we had all of our solutions, molarity, and solution information. And all of this information is on the syllabus. I know you all feel better when I say it out loud, but it's on the syllabus. So you don't need me to say it. You can just check the syllabus. It's there. Okay. Now, let's go ahead and look at some questions. What questions do we have? I can start with broad concept questions. We can start with specific homework questions. I did misspeak in class on, oh no, in the email I sent out that said all of homework 3 was valid. I missed the fact that 4 of the problems at the end had magnetics in it, and we didn't get to magnetics like I thought we would. So those questions about paramagnetic and diamagnetic will not be on the quiz. Question?
Yeah, so I have a question about number 4 on homework 3, talking about the off-ball principle.
Yeah.
And I don't know, I found it kind of
I
understand the concept, but then the question is, how does the principle lead to the formation of the periodic table? So I don't know if you can expand and kind of review.
Yeah, so this is a pretty big question. And this question kind of gets at the activity we did in class with the electron configurations. So what we have to realize is that it's not a direct connection. The Aufbaum principle leads us to electron configs, and that is what leads us to the periodic table, right? There's this in-between step. Now the Aufbaum principle pretty much says we're going to fill our lowest energy states first, and then we're going to build up from there. And all of the exceptions we saw in our electron configurations for the transition metals, for there's a homework question that asks about a weird exception. All of those are because the energetics of molecules or atoms with a lot of electrons is a little bit more complicated than what we've been doing. But what we've been doing works 95% of the time. 95% of the time. So it's okay if we gloss over some of those exceptions and gloss over those like nuanced details that get us that last 10%. So when we think about how the Aufbaum principle leads to electron configurations, the Aufbaum principle is essentially what tells us we need to fill the n equals 1, then the n equals 2, then the n equals 3, down this direction, right? It tells us the order in which we're going to fill the electron configurations. It essentially allows us to define the ground state electron configuration. And that's the other kind of important thing. The periodic table isn't just any electron configuration. It is particularly ground state. It's particularly the ground state electron configurations.
And by ground state, you mean
lowest energy.
Lowest
energy, which you could argue is also most stable. It depends on how you want to define stability. But in a physics sense, lowest energy is typically the most stable. In chemistry, we're going to be thinking about radioactivity, reactivity, and all those other things are most stable. So it could be more complicated, but energetically most stable is the way I would put it. Right? So we're looking for those things that it's also the things that tend to exist at room temperature, the things that we tend to see in the natural world. And that's where chemistry gets really different from a lot of other material. Like a lot of people like to compare chemistry to mathematics, but mathematics is very esoteric, very intellectual, very just kind of like making up numbers. Everyone's put in other space. Whereas chemistry is like, no, we're trying to describe the physical world and what we observe and the things that we see. So we're looking for these things that we observe in the natural world. And that's where we get this idea of the ground state electron configuration. And our energy filling is what gives rise to our, from the Aufbau principles, what gives rise to the electron configuration. And then we use that, and it would be really complicated for me to try and explain how these three things go together if we didn't do the electron configuration activity, where we arranged it ourselves, right? So I don't need to explain what the electron configurations look like and how they arrange to the periodic table. You all saw that. But if someone from another class is watching this, then it's like, whoa, why are these two things related to each other? And it really has to do with those valence electron shells, right? What's that last electron in the outermost electron configuration for the element? And then the periodic table is an arrangement of those. But the way we get the electron configurations is fundamentally from the Aufbau principle and finding those lowest energy configurations.
Yeah, I said the rows of the periodic table correspond to the n value of the configuration, and then the columns correspond to the last number of the last term in the electron configuration.
Yeah, and that's essentially that's correct, right? The rows is the first thing. The rows are just the n values. The n values are defined are the principal quantum number because they define the biggest kind of largest features of what's going on. And that defines the bulk of the energy. But then we also need the L's and the M sub L's to get our columns correct, to get our little bit more detail in terms of how we arrange things.
Isn't the n value not specifically based on the rows because of the d orbital in the fourth row?
Correct. Right. So that's the lag behind idea. And again, that gets into some of that greater detail that we're kind of glossing over of, well, that the Aufbau principle actually takes into account of like, well, why do we do 4s before 3d? Fundamentally, it has to do with the energy of interaction. When you have that many electrons around a nucleus, interacting not just with the nucleus, but interacting with each other, how does that change the energy of those orbitals? How does that change which energy is first? And the thing that's really interesting is, and we're going to talk about this today, I'm getting a little bit ahead, but that's okay. So when we go 4s to 3d, I'm just going to pick 3d6. I don't even know what element that is. I've got a periodic table here, so that's 1, 2, 3, 4. Oh good, it's iron. I picked iron. That's the one I was hoping I would pick. Iron or cobalt, those are both interesting. When we lose electrons, so we know we fill the s orbitals before the d orbitals. But in putting the s and the d in, when we start filling those d electrons, that actually shifts the energy of these orbitals. And when we lose electrons to make ions, so this would be argon. This would correspond to iron. And if we wanted to make an iron ion, we're going to go over this today in class, but I think it does a really good job exhibiting how this gets more complicated and how we miss things. We lose the s electrons first. So you end up with 4s0, 3d6 to get your 2+. And if you're like, whoa, that doesn't make any sense because we filled this first because it's lower energy, the energy levels are changing as we put more electrons in. And that makes it so when we start losing electrons, we're actually going to lose them in a different order than we filled them.
So you lose the ones with the higher n value.
Yes.
Okay.
Now, I also want to point out that even representing electrons as static objects in particular orbits is a bit of a simplification. But it's an important one because it allows us to kind of, again, get 85% of the physical properties we're trying to talk about. We can explain with this static picture. Yeah.
Would we need to keep the empty 4S shell?
No, a lot of times people will just put this as 3d6. I like to explicitly put the 4s0 so that way, and this is kind of for educational purposes. You would not put this in like a publication. You probably wouldn't find it this way on like a Wikipedia article or any textbook. I like to put it explicitly for educational purposes of like, oh, that's where the electrons were lost from.
In a similar vein, how do we do the electron configurations when we lose maybe like one electron and it's 3d5? Do we just make it we fill in that from the 4s, right?
Yeah, it would be 4s1 3d5. So that would be looking at something like manganese. No, we're getting into today's lecture at this point, which I'm okay with.
It's on
If
the
you all.
homework,
Yeah, I don't know how much it has
Okay.
stuff like that.
Hey, does it have the transition metals?
I
something
think it
with
had
the-
one.
But like you have to like fill in the little pairs of electrons.
Yeah.
First or the
Yeah.
stable.
I kind of want
How does that
to.
work?
Does anyone have a printout of the homework handy?
Yeah.
I
So
had no idea.
I think it's one of the four that you said we didn't cover yet.
Okay.
Yeah,
Was it the
so
last four?
you can calculate
You
the
said we didn't cover
wavelength. but
Anything that talks about
technically
magnetism.
that's enough.
Yeah, that's what it is.
But there are some problems that ask you to do electron configurations. There are some problems that ask you to do ions, but I don't think there are any problems that ask you to do transition metal ions on the homework.
There's a cobalt 3 plus,
Ooh, which problem is that?
number 12.
Number 12. What's the problem say?
Problem says write a condensed ground state electron configuration for each ion and identify it as paramagnetic or diamagnetic.
Yeah, so that one wouldn't be on quiz, but let's go ahead and look at it. Cobalt is argon. And the way I do these, I always start with the neutral atom and then I think about where the electrons are lost. So it's argon 4s2 3d7. When I go to 3 plus, cobalt 3 plus, I'm going to lose 3 electrons. I'm going to lose the 2 s electrons and 1 of the d electrons. So I'd have argon 4s0 3d6. Now, the other thing that I was going to, when I was like, oh, we're getting into the lecture material for today. Again, in trying to describe what we observe in the physical world rather than what we can just generically write down, like what we could theoretically write down, there is, cobalt has a lot of different oxidation states, which is the old term for charges. And what we see here is we have the 3 plus. Why don't you see the 1 plus? Why don't you see the 2 plus? It's that kind of what can we write down theoretically versus what actually exists in the world. For example, going back to the iron example, why do we see iron 2 plus, iron 3 plus, and not iron 1 plus? Fundamentally, it has to do with energetics and the way and the fact that we're in an oxygen-rich environment, a water environment in the world where we are, and that makes it so iron 3 plus is really common. Iron 1 plus doesn't really happen. Yeah.
When you get into say ions within f orbitals, how would that work? Because if it's by energy or by the n value, it would have to go back two.
So do you want to
energy
look
levels.
at an element that is an F block element, or do you want to look at something that's like a D block that has a full F shell?
Probably D block has a full F shell because that'll do the same thing because F comes before D.
Yeah. So if we looked at I'll do you one better. We'll look at something quite strange. Let's look at Let's look at lead. Lead or bismuth? Which one do you want to see?
Lead.
Let's do lead. Oh, that pen's dying. The chemistry department stopped buying green ink, so I have to order it myself now. Because I like my green pens. They're like, just stop using green pens. I'm like, but I like them. Okay, so lead. We're going to have xenon. We're going to have 1, 2, 3, 4, 5, 6. 6s2. 4f14. 5d10. 6p2. Now, when we've got the D's and the F's completely full, they are more energetically stable.
Okay.
Right? So this is, again, that idea of as we put electrons in, the energy levels of these things are actually shifting and changing. So when the F block and the D block are full, they actually stabilize in terms of their energetics. They become energetically stable. So if we formed lead 2+, in this case, again, it just has to do with the energy. We're actually going to lose the p electrons first. Then we'll lose the s. Then we will try to lose the d, but when we look at the energetics of losing those d electrons today in class, we'll see that losing those d electrons, losing anything that's kind of like a closed shell or a core electron, is very energetically unfavorable. And, you know, we can think about this in terms of why do we see lead 2+, lead 4+, but we don't see lead like 14+, right? Lose all of the s electrons, all of the p electrons, and all of the d electrons. We can write that down on paper, of course, but you don't really see it in the natural world. We don't really observe that. We could theoretically make lead 14+ in the laboratory. It would be very reactive.
Isn't 4F14 like a full energy shell sort of thing too, though?
Yeah.
So like, how do you know which one is harder to take out an electron between 5d10 and 4F?
5d10 and 4f. Well, first off, I've already said I'm not really going to ask you questions about f block elements. Like that's more advanced. But we would go with the n values. So the 5d is probably going to be easier to remove electrons from when we go to that removal step.
Would it be kind of the idea of like the valence electrons? So you really just when you're talking about like the ones that leave the atom or are gained in the atom, it's just in the valence shell, which usually is just S and P.
Yes. SP and an unfold D is also considered valence. Valence is a tricky word.
Okay.
Valence shell really refers to the electrons that give rise to the reactivity of the element. And so it's considered any s orbitals, p orbitals, pretty much anything that's like an open shell, that is to say, p orbitals that don't have everything, that are empty. S orbitals are kind of always reactive because they're so far from the nucleus. D orbitals can be reactive if they're not full, but once they're full, D's and S, once they're full, are not very reactive, so they're not really considered valence shell.
Mm-hmm.
For us, in our simple kind of understanding of it, I'm pretty much going to say everything past the noble gas. So for me, it becomes a definition of, well, what's core electrons, what's valence electrons. And for me, anything in the noble gas configuration is core electrons. These are all kind of valence electrons, depending on the definition of valence electrons you're using. But the S's and the P's are the most reactive of those shells because they're furthest from the nucleus.
Okay.
So they are what we typically think of as the valence shells. But D's, if they're not full, are also reactive, can also be considered valence shells.
Mm-hmm.
We haven't gotten to that. Again, you're all going to be bored in class today. I'm going to be going over this, and I'm going to expect all of you, I see your faces, I'm going to expect all of you to raise your hands and be like, I know the answer to that. Question?
So with like manganese, where it's argon plus 4s2 3d5. When one of the electrons from the 4s shell go down and fill out the lower energy level? Like, I thought there was some rule about that.
That was only true for a couple elements, and that was a special rule. Do you remember the name of it? The
Is
name
it
describes it.
the exclusion rule or?
Half shell or the full
Half shell, full shell.
Yeah. So.
So when your
do you
d orbital is almost half full, that is to say d4s, it will steal energetically. An electron will transition from the s to the d, so you've got s1 d5. So both your orbitals are half.
Okay.
The same thing happens when you're at the d9s,
Right.
because then one electron moving from the s to the d would make it so you have a s1 d10, and that full 10 electrons creates
Okay.
extra stability.
And what about with like 5d3? Would it just stay the way it is?
Stays the way it is. The energetics of taking 2 electrons out of the s orbital doesn't work out. Right, and this is part of the reason why I only asked you to remember 5 exceptions. Right, and if we're looking at the periodic table,
It's chromium and MO. or
it's
whatever.
copper, silver, gold, chromium, and molybdenum. It's the D9s and the D4s. Those are the only ones that we have to remember. There's actually, to the trends that we learned in terms of electron configurations, there's actually there's quite a few exceptions based on the energetics. Especially when we start talking about ions and how ions form, there's a lot of different energetics that we're going to kind of gloss over to just get the broad kind of trends. The same thing we did with our periodic trends of radius. Our periodic trend of radius is like, these are small, these are big. And that's generally true, but there's a lot of exceptions in there that are the nuanced details of energy and interactions.
And how come that doesn't apply to W and SG? I don't.
To tungsten and seaborgium?
Yeah.
Tungsten and seaborgium have some extra complications because the f orbitals are also playing a role.
Okay.
So those do have exceptions as well. I'm just not asking you to know about them.
All right. Sounds good.
Cool. Yeah.
So, what if you like those element that's right next to one of those, and it gains or loses an electron?
To form an ion?
Yeah, to form an
Okay.
ion. Like let's say it adds an electron to that,
Okay.
and then would it lose an electron from the S shell, and then have it get a half shell in the upper one?
So, this is a very interesting question. It's not very physically relevant, and I'll explain why. We'll look at, I think, that the situation you're talking about. I wish you'll ask questions like this during a lecture, man. This would be great. Yeah, everyone's like, oh, office hours are great, lecture's so boring, and it's just like, no one asks questions during lectures. Y'all just kind of sit there and like, yeah, great. I think it's the size, but let's say we're looking at something like vanadium. Vanadium is argon 4s2 3d3, right? We look at this and say, oh, is it going to steal 2 electrons? Are the 2 s electrons going to transition to the d orbital to make it more energetically stable? And it's like, no, that doesn't work out that way. The energetics, which we would get through doing a quantum mechanical calculation or through an experimental observation, the energetics suggest that this is the way it would stay. Now the question of what if we went to vanadium minus? The transition metals, because of the energetics of the orbitals, the ionization energy versus the electron affinity, vanadium, like none of the transition metals pick up electrons. None of them have negative charges. They only have positive charges. If we look at the periodic table, and we're going to do this today, again, we did it a little bit already, but if we look at the periodic table, pretty much the only things that get negative charges are the things over here. The things that have very high electron affinity, those things that want electrons, right? Everything over here has relatively low electron affinity, which means they're not going to attract electrons. We're going to combine the idea of electron affinity and ionization energy into the idea of electronegativity. And we'll just go through that definitionally. If there were more people that were going on to later chemistry classes, Chem 126, Chem 312, stuff like that, electronegativity would be a much more important thing I'd spend more time on. But with a lot of you just having this as your only chem class, electronegativity is just like, cool, it's a way to combine ideas.
As far as the midterm, would you expect the questions to be a lot like the homework? Or,
No.
What would the questions be like? Would they?
More like, so the homework has, the homework does a good job kind of covering a lot of topics and asking some decent questions. I ask some questions that are similar to that. However, the worksheet questions are, I didn't write most of the homework questions. Typically the most difficult homework questions are the ones that I wrote. So if you're like, well, that homework question was hard, that might be one I wrote. The exam questions, the worksheet questions are actually old exam questions that I stopped using and moved on to worksheets so people could see my question style. For the multiple choice questions, those free response questions are not off of old exams. Those, well, some of them are just kind of things that I thought were interesting that combined ideas. So I feel like the worksheets give a better sense of the types of questions I might ask. And I should update those worksheets to include more of the calculational problems. But the exam will be split into 3 kind of sections: short multiple choice, long multiple choice, and free response. So it's like concepts and definitions, calculations, and then a combination of those with concepts.
A lot of that stuff is found in the book, right?
A lot of it's found in the book. A lot of it's found on the lecture slides. A lot of it's found on the worksheets, on the homeworks. Yeah, there's a lot of places where you can get a lot of that.
Is there anything that is specifically only in the book that we need to know? Like, cause
There could be.
Okay.
Some of the definition, there's already been several times in class, and only in the book is where I kind of pause, right? Because there have been several places where I've brought up terms in class that I've assumed everyone already read. Like when I started talking about valence electrons, ground state configurations, things like that. Those were vocabulary terms I didn't explicitly define in class. I assumed that they were read in the textbook. But they did come up in class as well.
Okay.
But I never defined them. So is that exclusive to the book or not?
I'd say probably.
It's a
not.
gray area.
Yeah.
So I don't think there's anything that is explicitly exclusive to the book that I haven't brought up in class. But you could also argue with me, and I will definitely. Part of the reason I don't do study guides and I don't do like practice exams and things like that. I've had LAs make practice exams before, but they're nothing like my tests, and so students. If I don't have something on the study guide explicit, and then it's like kind of maybe on the exam because it's like related to one of the ideas, I get students really angry at me. I've like my first 2 years I was doing study guides and things like that, and students were furious. They were just like, "You didn't put this on the study guide," and I'm like, "It's related to this thing." They're like, "But you didn't put it explicitly." It's just like, I mean, I've also had subjects where it's like, I very clearly defined valence electrons in class, actually, and I'll have students be like, "No, you didn't." And I'm just like, I swear I did. They're like, "No, you didn't." I'm like, "Okay, I can't. If you don't remember, I can't do anything about that." So I'm like, "Were you on your phone? Because you might have been on your phone."
So,
So it becomes difficult to say, is there something in the textbook that I haven't explicitly mentioned in class that could be on the exam? Maybe, but that's just to cover my bases.
Yeah.
Right? I try to make sure anything that I think is important that's worth testing on, I mention in class or in one of the labs or in one of the homeworks.
Mm-hmm. Got
And
it.
it's not just in the textbook. Do we have other, like, this has been a lot of conceptual work, a lot of kind of like test structure questions, exact homework questions or anything like that? Yeah.
I have like 12 like D, just that like it's like kind of a similar question to the last one.
Is that a magnetism problem? Yeah.
Well, so the interesting thing about 12 is it's a magnetism / not magnetism problem. You can write the electron configuration and not do the magnetism,
I'm
right?
just wondering about the electron configuration.
What was the element 12D?
It was Ag plus.
Ag plus. Okay. Now, I always, in a learning sense, I will start by doing silver, and then we will look at which electrons we lose. I will do this in terms of the electron configuration and the orbital diagram. Silver is krypton. Thank you.
Okay.
Krypton 4s2. Oh, sorry, 5s2. 5s2. 3d9, and we all go. Oh yeah, we're not gonna do a D9. That's our exception. Whenever we see a D9, we're gonna change this so it's a 5s1, 3d10. Get that full show.
Wait, what do you do? 4D10?
Oh, good
Yeah.
grief! Thank you. Yes, 4d10.
That would be very unstable.
Well, it does have the 3Ds. That's just not the ones that we want to show. So that was a typo. It should be 5s1, 4d10. Yes. So that's silver. It is one of our exceptions. Now we look at this and we say, okay, which electron is silver going to lose to become an ion, to become Ag+?
Is the S.
So you can put this as just 4d10, or as I said earlier, for educational purposes, you could put it as krypton 5s0, 4d10. Either one would be right. In my class, some other instructors say only this one is right. I think that's fine. Now, let me ask a follow-up question for all of you. How would you do silver 3+? And would you do silver 3+?
I don't know if you would or not.
So this is again the kind of can we write it down versus does it exist? Can we write down what silver 3+ would be? Yeah, of course. You take 3 more electrons out of the d orbital, you got 5s0, 4d7, silver 3+. However, we don't see that energetically in nature. There aren't a lot of things that are electronegative enough, that have enough draw of electrons to pull the electrons off of the closed d orbital. Is it completely impossible? No, I imagine that there's situations where you can make that happen in a laboratory, but in the natural world, we're just not going to see it. We're not going to see it happen. It's not what we call a naturally occurring oxidation state. So yeah, can we do it? Can we write it down on paper? Yeah. Can we make it in a lab? Maybe. Does it exist in the natural world? Not so much. Did that answer you? And then in terms of paramagnetic diamagnetic, this is going to be paramagnetic because it has one unpaired electron. This is going to be diamagnetic because all of its electrons are in twos. And we're going to go over those definitions today. Won't be on the quiz.
So in the quiz,
yeah,
I'm guessing that there will be some questions about just the electron configuration of an ion, but it won't be of transition metals.
That would I feel like that would be fair. I feel like that would be fair. Just remove that number of electrons, just go backwards. The transition metals is the only place where it's like, oh, we have a special order. And because there's a special order, I want to make sure I teach that to all of you before I test you on it. Question there, then there, yeah.
So for the Ag+, you lose, so if it's a plus, you lose an electron?
Yes. Because an electron has what charge?
Negative.
So losing a negative makes it more positive.
So if you're doing like phosphorus plus, then it would, and it's at like 3s2, 3p3, and you're taking off one electron, you would just get 3s2, 3p2.
Yep. Yeah.
Just a quick homework question. Just one part of A. It's 8A. It says from the given electron configuration, draw the orbital diagram, write the atomic symbol, group number, and period number. And then it's just neon 3s2, 3p5. I just want to make sure I was right.
Okay. So we're looking at neon, and what do we want to get for
We
this?
want to find the electron configuration and draw the orbital diagram, write the atomic symbol, group number, and period.
It told us that it was 3s2, 3p5?
Yeah, we don't have to find the electron
I was gonna say, it
configuration.
feels like they
So-
already
oh, sorry, I'm sorry. From the
From the electron configuration, good. So we want the orbital diagram, the symbol, and
group and period number.
okay. So orbital diagram's pretty straightforward. We've done this. We go neon. We go S block, P block. We go 1, 2, 1, 2, 3, 4, 5. To get the symbol, we look at the periodic table. 3p5 looks like. Wait, why can't I count? Chlorine. 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 That is going to be, in terms of group, I'm okay if you give the name of the group. So the period is, oh, now I gotta remember. 17. And the group is?
3.
If you put it as a halogen, I would also be okay with that.
So how do you do grouping and how's the grouping space out?
So, and this, oh, man, I should know this better, but the period is essentially the different columns, and the groups are the different rows.
Okay, sweet.
I want to double check that right now.
What's the period?
What's
What's
the-
what's the rows?
Did I? Yeah, I'm worried that I
Show
just
that?
flipped that.
I think so.
Well, as long as you ask
Yeah,
for
the
both
rows
of
were-
them.
The rows will appear.
The group is the column.
Double checking.
I think groups.
Yeah, yeah.
Period.
We got those flipped.
17.
Sorry about that.
No problem.
And I kind of, as soon as I wrote halogen, I was like, I feel like I flipped that. Yeah. Because we call it the halogen group. We call it the alkali earth metal group. Yeah.
Sweet, thank you.
Yep. See ya.
When we do
And
that,
that's on video.
do we need to label like which orbitals they're on, like the 3s2 or something like that?
What was the question?
We don't need to do like 3s2 between like below the neon thing. Or next one. Yeah, for the orbital diagram.
Oh, for this? No, it would be good to label that.
But we don't need to.
I would encourage you to.
Okay.
I think that's important.
A couple questions. So for the orbital diagram, on the homework it says draw the orbital diagram, and then so I thought by that you meant like the shapes. Are we gonna have to do that?
No, so that would be drawing the angular distributions.
Okay, are we gonna have to do that?
I might ask that in the future.
How would you know, like for the ones that are figure 8, how would you know if it's on the X, Y, or Z?
I would ask you to draw all three.
Oh, okay.
Yeah.
Okay. And then
And the reason I would ask you to draw all three is because it turns out that there's not a direct correlation between the M sub L values and the physical representations of them.
okay, that's what I was wondering.
Yeah.
If
There's-
we need to know the clue. Okay.
Yeah, you don't.
And then for the for saying that the group is halogen, what
Mhm.
about like where the transitional metals are like in more than one technical
That
group?
there you would want to do the numerical value. There's only a few where you could use the names of them. That's the alkaline metals, the alkaline earth metals, the halogens, and the noble gases.
Okay.
all
Other
have
than that,
very-
we just have to say the number.
Yeah.
Could you maybe do number 15?
Sure. What is number 15?
It says the energy difference between the 5D and 6S sublevels in gold is what gives rise to its color. Given that this energy difference is approximately 2.7 electron volts, explain why gold has its yellow color.
So, what are the essential things about this problem?
The EV
Delta E. Is this
and the change in orbital.
delta E would be 2.7 electron volts, and wouldn't we want to convert that into joules so we could use that constant. What's it called? The Rydberg constant. The Rydberg constant.
So, we could, but we've already got the delta E. Do we need the Rydberg equation?
Oh,
You could just use
Maybe not.
HC over.
Apparently
oh,
not.
HC over lambda.
Find the wavelength. Right. So this is one of those things where it's very obvious that students overcomplicate problems. Right. You see that it's 5D to 6S. You're like, is 5 to 6? That's a transition. I should calculate the transition of that energy and
Would
see
get the same
what's
number.
going on. Not exactly. Right. Because if you used the Rydberg equation and used 5 to 6, you'd be doing that for the Rydberg equation that works for hydrogen, not for gold. You'd have to know the Z effective for gold. So something that we could do that would be interesting would say, oh, given that this transition is 2.7 electron volts, what's the wavelength to get us the color? What's the Z effective in gold based off of this? Right? So we could do delta E atom equals HC over lambda, absolute value delta E atom. It's emission, so we're okay. You could also do delta E atom equals Z effective squared, Rydberg negative Z effective squared, Rydberg constant, 1 over n final squared minus 1 over n initial squared, and say that our we've got this transition. This would be an absorption, right? So if we're looking at the magnitude of this, we're going to get something that's going to be positive for the atom because it's an absorption. Which means we couldn't use the other Rydberg equation because the other Rydberg equation only works for emission. Rn final is going to be 6, Rn initial is going to be 5. We could calculate a Z effective from that and say, oh, what's the Z effective? But you would need you need that extra information. Yeah.
If we wanted to solve for the wavelength, would we have to take that 2.7 electron volts? Would we have to convert that, or just leave it?
Ooh. What are the units of Planck's constant?
Joules, seconds.
Yeah. So the problem is, if we look at this and we have 2.7 electron volts, it's equal to 6.626 times 10 to the minus 34 joules seconds times 2.99 times 10 to the 8 meters per second divided by unknown meters. Right, the way that this is going to work, you know, seconds cancels out. I'm going to bring my question mark over, my electron volts down. Question mark meters is equal to 2.7 electron volts. Are those units going to cancel out? I would say just convert the electron volts to joules and you're good. You could if you wanted to be more complicated. If you wanted to be more complicated, you could convert Planck's constant to electron volts. But why would you do that? You could, but why would you?
I did that and I got 459 nanometers, which is like per joules.
Yeah. So let me write this 1.602 times 10 to the minus 19 joules.
Oh, does that mean it absorbs purple?
Yeah. Right? So you did this calculation, you got 430?
459. Yeah.
459 nanometers. We look on our visible light spectrum, we say, oh, that's going to be purple light. It's absorbing purple light, which means it's going to appear
The opposite color on the color.
yellowish. Yeah. it's gonna have that yellow sheen to it. If you were going into 125, we'd get to talk about why I think gold is considered valuable. It doesn't tarnish. If you look at the reactive properties of gold, it's not very reactive compared to the others. It doesn't. It's very difficult to oxidize gold. So when you make a piece of jewelry out of gold, you know, silver doesn't tarnish that much, but if you get old silver, it does tarnish. It's got like that grayish layer on it, and you gotta polish your silver. You don't really have to polish gold. Gold doesn't tarnish for like hundreds of years. I mean, even when they open up like tombs that have been like sealed for thousands of years, there's not enough oxygen in the rooms to even like cause the gold to tarnish. It's like still super shiny. Keeps this luster really well. Super, the other thing that I think makes it valuable is the metallic properties. It's super flexible. It's really like, if you actually have like pure gold, is actually almost soft. It's pretty easy to dent. It's pretty easy to shape in terms of other metals. It's even like ancient civilizations had to mix other metals into their gold to get it to hold its shape better. But that makes it so you can do really delicate, intricate work with it that you can't do with other metals. Question?
3B on the homework.
3B. What is question 3B?
How many electrons in a single atom contains each of the following quantum?
Yes.
Yeah.
So how many electrons can have a set of quantum numbers? Let's do some logic before we get into it. If 4 numbers are defined,
1.
that defines 1 electron. If 3 numbers without m sub s defined,
It's 2.
it's 2 electrons. Right? Those things are always true. It gets more complicated when we get to if
2 numbers.
L equals 0 without, sorry, that should be without m sub s defined. Without m sub L or m sub s, if L equals 0,
2.
it's 2. If L equals 1,
6.
if L equals 2,
10,
if L equals 3,
18.
if only n's defined,
Wait, if it's 3, shouldn't it be 14?
oh yeah, sorry. Sorry about that. 14, and then I think G is 18. If only n is defined, it depends, right? If n equals 1, then you're just in the L equals 0. If n equals 2, then you've got 0 and 1. If n equals 3, you've got 0, 1, 2. If n equals 4, you've got 0, 1, 2, 3, so on and so forth. So with this in mind, we've kind of got some logical framework, some conceptual understanding, some rules understanding of how this all works. Now let's look at the actual problem. Part B says
5p.
5p. So what we have to realize here is that this tells us n is equal to 5, and the p tells us L is equal to 1. That means m sub L is unknown and m sub s is unknown. In this situation, I can also think about it in terms of 5p. How many electrons fit in those boxes? 6 electrons.
Okay.
Are we doing this one?
Yeah, did you want to
Yeah,
see any
yeah,
of the
no,
others in the problem, or
that's
just
it.
that one? Just that one, okay.
Could you do 11, which it says arrange each set of atoms in order of increasing ionization energy?
Yeah.
So they have like a B and C and D.
See. Which one do you want to see?
Yeah, I'm gonna just do.
Just pick one of them and tell me the elements.
Yeah, so I wish I knew my elements, but SR, Ca, and Ba.
Strontium, calcium, and barium. So we're going to do this just based off of the periodic trends. We're doing ionization energy.
Yeah.
And do we want this to be increasing or decreasing?
I think it said decreasing ionization energy.
Every time
See ya.
Of increasing. So
Oh, that would give us the exact opposite of the right answer.
increasing ionization.
Or they use the trends.
Yeah.
We only do this based off of trends, not exceptions.
Right. So we're just gonna go based off of the general trends.
And will we ever have to memorize what the exceptions are?
What do you mean the exceptions?
Isn't there like exceptions, like a certain row like tends to have like
For atomic radii,
For I guess for everything there are, but we didn't learn any specific exceptions, right?
yeah, they did mention a couple in the book. And
They
I'm
mentioned a
just
couple
like,
in the book. We mentioned a couple in class. For these ordering questions, you won't need to know the exceptions, but I could also do questions that are like, this is an exception to this trend. Explain why.
oh,
Right? It would be more specific.
but like ordering, you like
Ordering, we're going to go with the general trends.
should I write based off of the trends?
Yeah.
And then this.
So ionization energy, where's our smallest ionization energy?
To the bottom,
Bottom
right or bottom left. I don't know.
And our largest ionization energy?
The other side.
Right. These things over here are want to hold on to their electrons more. It's harder to take the electrons away. These things down here, it's easier to take the electrons away. Our general trend is this direction, generically, right, broadly speaking. So then we want to look at where these things are. Oh, and look at that. Calcium, strontium, and barium are all alkaline metal or alkaline earth metals. They are all lined up right on top of each other. Calcium, strontium, barium. So if we wanted to do order of increasing ionization energy, it would be barium, then strontium, then calcium.
Is there an electron affinity question?
No, because electron affinity is a pretty bad trend. There's too many exceptions to it to make a good trend out of that one, as far as I'm concerned.
Okay.
Ionization energy and radius, they're pretty good trends. Ionization energy is pretty good. Radius is really good in terms of being a trend.
For the 4 topics that we did, it was like atomic radius, ionization energy,
Electron affinity.
electron affinity. What was the other one? Ion radius?
No, we did the periodic table. Oh, the ones that we were going to talk about in class?
Yeah.
Ion radius we didn't do in our activity, and we're going to talk about that today in class.
But like, do they all? So the 2 that we learned about move in
3.
the opposite direction of atomic radius.
Yes.
Is that true for all 3 of them? The ion radius.
No, ion radius doesn't have a good trend. It's just something else we want to learn about.
Okay.
So ion radius kind of has a good trend, but it takes more thinking to get it right than just having a trend.
Okay. Thank you. I was just gonna use that as like reference. Like it's always the opposite of the radius.
and electron affinity is the same.
Same directional, but
Direction.
opposite sign. So ionization energy is energy we put in. So the ionization energy is a positive value, energy we put in. Electron affinity is a negative value because it's energy that's released when an electron is attracted in. But if we're going with magnitude, that follows the same magnitude trend. Smallest value, smallest magnitude, largest magnitude.
And so for an ordering question, it would be in the same order. Like
Yes, yes, yes. Yeah.
We already talked about 15 and or
Yeah.
5 today.
Yeah, we haven't done number 5. Let's do number 5, and then let me check if there's anyone asking questions online. Sometimes people watch online. Right. Not today. Today, no one is watching. Let's do number 5, and then I'll go ahead and stop this video and post it in the hopes that people watch it. So what's number 5?
Number 5 is write a full set of quantum numbers for each specific electron in, and then there's 5 cases.
Oh, right.
There's like the outermost electron in a rubidium atom.
Which one would you like to see out of those?
Probably either B or C. The electron
Probably
gained
C.
when sulfur or negative sulfur ion becomes a
We did?
Because it's sulfur. We did.
Oh, we did that yesterday. We didn't do that today. So I don't have it on the video. I could do that today on the video. What was B?
do you want to read it?
Was it fluorine or sulfur? Just what?
Sulfur.
What was C?
Sulfur, silver.
Silver.
Oh, wait, yeah, silver. The electron
We did
loss from the
silver with
silver
the
atom
49.
is.
Oh, we did
Yeah.
silver.
Yeah.
Let's do sulfur. So let's do B.
Okay.
So, again, the way that I think about this, I always think about it in terms of writing the neutral element first.
Mm-hmm.
So sulfur is going to be neon 3s2 3p4. I'm looking at the periodic table correctly. Yes. If I wanted to do sulfur minus, which isn't actually stable, I do neon 3s2 3p5. If I want to do s2 minus, I would do neon 3s2 3p6.
Okay.
In order to get the quantum numbers, though, this doesn't really give us all the quantum numbers. It's better to look at the orbital diagram.
Okay.
And these all start out the same way. And what it's asking for is the quantum numbers, this last electron that goes in. Right? That sixth electron. So we have to know a couple things, right? We have to be able to write down the electron configuration. We have to be able to relate it to the orbital diagram. We have to know how the orbital diagram relates to all of the relevant quantum numbers. What's the n value equal to?
3.
What's the L value equal to?
1.
What's the m sub L value equal to?
1.
Why is it 1?
Negative 1, 0.
Right. We always start at the negative side, count up to the positive side. Different classes might do that differently. What I mean by classes is I know upper division physics, when they start talking about atoms and molecules, will do a different ordering of their quantum numbers. They like to do 0, minus 1, 1, 0, minus 2, 2, minus 1, 1. It has to do with when you're writing down, like, because remember, these are all representing functions. These are representing mathematical functions. And when you start writing down the functions that they represent, it comes out a bit nicer if you change the order. But in chemistry, we do this one. And the m sub s,
Is it negative 4.5?
ooh, which is it, negative or positive? It's negative. I thought I heard you say positive 1/2 for the first time.
Oh, no.
Okay,
How
sorry, I
would
just
you
didn't hear you.
tell?
Is the arrow pointing up or down?
Yeah, so it's like the last one, whatever it is.
Yeah.
Okay.
How did you get the L value?
Yeah.
That's
The L value,
confused about.
we're in the P block, right?
Oh,
So this was something I said in class, make sure you write this down. It was on the lecture slide. I said, make sure you write this down because this is something I expect you to memorize. And I don't like memorizing things, but this is just a naming convention. Naming conventions, vocabulary, we kind of have to memorize that stuff. S is L equals 0, P is L equals 1, D is L equals 2, F is L equals 3.
okay.
You have to have that memorized.
And this is just basically for the last line that you drew.
Yeah, the question was asking for the full quantum numbers for the specific electron. And that was the electron specified.
And then the N value just comes from the row.
Yep.
Right?
Well, also from the quantum number up front here.
Okay.
For number 2,
Yeah.
it says define shelling and effective nuclear charge.
Uh-huh.
What is the connection between those two terms and what properties do the atom will impact each term? And then it was basically in the textbook, it had like a little equation, and like shielding was like when an electron's further out, it's affected by the other electrons, and like so like further away, and the effective nuclear charge basically is like an equation with like something in it.
We can just do it conceptually though, right? We're not looking for the mathematics of it. We're looking for the conceptual definitions. So if we're looking for the conceptual definitions, we can say shielding, and it turns out that effective nuclear charge and shielding are like two sides of the same coin. Shielding is how much the inner electrons block the outer electron from seeing the nucleus, And effective nuclear charge is how well the outer electron sees the nucleus in terms of the forces of attraction. So shielding is the process of what the inner electrons are doing. Effective nuclear charge is the process of what the nucleus is doing, all relative to that outermost electron.
For number 12, it says right.
Yeah, I'm gonna stop the video now because I feel like we're starting to repeat questions a bit.
Gotcha.
So.